So in the previous video, we stopped here where I showed you the equations for flow rate. It could be applicable to gas to oil. Nobody cares about producing water in oil and gas industry, so typically oil and gas. And then you can integrate these equations and obtain the cumulative production. And I pointed out you just need to integrate between time 0 and t and with respect to time. So what if we actually do that for one of the models? So here I'm showing that cumulative production can be obtained by integrating it analytically. When you integrate analytically, what you're doing is an exact integration. And when we integrate numerically, it is approximate. And we'll talk about that later. So let's start with the analytical integration of the exponential decline model. So we want to find out cumulative production given the equation for flow rate. So cumulative production is always integral of flow rate with respect to time, from time 0 to t. Very important. If you forget to integrate within a time interval, meaning if you do an indefinite integral, you wouldn't get the same result. So to get the expression for QP, meaning cumulative production, you will need to make it a definite integral. So the question now is, what model do you want to integrate? And here we want to integrate the exponential model. And what's the equation for the exponential model? Q equals QI exponential, that's what I gave you in the previous slide, minus DIT. So you just put in this value into here. So that's the equation given on the previous slides. So you need to just integrate this, right? So integrate this from 0 to t. That's what you're going to see here. Integrate from 0 to t, expression for exponential integral with respect to time. So when you integrate this, what do you expect from calculus? QI is initial flow rate. Does initial flow rate change through time? No, it's initial value of flow rate. So because it's constant, you can take it out and put it outside of the integration, right? So what's the integral of E minus kx, for instance, dx? That's what you need to be able to integrate this. Except that x is t, right? So E minus kx, who knows what the integration should be? Well, before we get there, I already explained you take this QI, because it's constant, out of the parentheses. That's what you see here. This is actually where we evaluated the integration. So we know from calculus that this integration is going to be minus, right? Because you have a minus there. Here, oh, whatever I wrote was lost. But basically what we are trying to do is integrate E. Let's even start simple. If you integrate E kx with respect to dx, what do you get? Right? So if it's E minus kx dx, the minus stays. So it's minus 1 over k E kx. So dit dt, that's what we're doing. So it will be minus 1 over di e raised to power minus dit. We add qi outside of the parentheses, right? So this will be qi times 1 over di, so that's minus qi over di, and then we have our exponents, which we can write out in this form, right? Same as this form. So that's how we get this. Are we done? Remember, you're integrating between this range. So all of these has to be from 0 to t. So you will substitute t into this equation, get the result, and then minus that. So that will be minus qi di, which is not a function of t, right? And then exponent of minus di times t is the upper limit, minus the same thing, right? Except that t is now 0. So when t is 0, di times 0 is 0. So exponent of 0. Anything raised to the power 0 is 1, right? So e raised to the power 0 is 1. So this term will become 1. Whereas this other term remains the same. So minus 1. Put it in the big square brackets. And this is minus qi di. We're almost done. This di, we're going to just continue this way. We can write it out as, first off, let's take this minus into let's multiply through by minus. So take this minus in, so that this will become plus 1 minus that, right? So we can have qi over di. All right, since we're going to continue working on this, we can bring it up here. So it's qi over di exponent minus dit. Oh, I meant to do the minus first. Minus times minus, so it's 1 minus the second term, right? That's what I meant to do first. And now this d1 over di multiplies everything, right? So technically this is equivalent to dividing through by di, and then this qi times 1 is qi. What's qi exponent minus dit? Does that look familiar, this term? Yes, it does. It's precisely this. So in place of qi exponent minus dit, you can use q, because that's the expression for flow rate based on the exponential decline. So this is basically equal to qi minus q over di. And that's your qp. And if you go back to the previous slide, that's exactly what we showed as cumulative production. So I can clean out all of this calculation. It's a video, you can pause it and make sure you can do this derivation. Just some basic calculus, right? So this is what I did. Lower limit t is 0. Exponent of 0 is 0. Sorry, exponent of 0 is 1. And then raised to the power 0 is 1. And then we substituted this one at the very end, and we got this expression for cumulative production as an integral of flow rate. And this procedure will work for any equation of Q, except that some Q's could be very complicated and there is no easy way to integrate it. And that's when numerical approaches, numerical approximations, that's when they come in handy. Good.